Okay, so what I need to do, what is the first thing you need to do anytime you see something with an angle? Yeah, crack it right away, right away. And because I know 3, 4, 5 trunk, and it's acute angle, then this is going to be 0.8, so this is like 48, and this is going to be 0.6, so that's going to be 36 meters per second. Okay, your answer is going to vary slightly. Your answer is going to vary slightly, you know, but whatever. I'm doing this without a calculator, so we're just going to round it that way. Now, do you see that that means the horizontal velocity at the top is 48 meters per second? And the vertical velocity at the top is, of course, 0. The vertical velocity at the top of any projectile motion path is 0. Right? The horizontal velocity stays constant the whole time. So now I have everything I need to do this. Do you see that? So I just have an initial, instead of saying on your desk, remember I said on, it was sitting there, the initial velocity was 0. I just have an initial velocity. That's it. I use the same equations, I just plug in some extra stuff. So this is going to be fine. We're going to be okay here. What we have to do now is they want to know how far from its initial they land. So they want to know this. Now here's my question: does it land the same or farther than the rocket?
But
Why do you say farther?
because it like push, boom, and just went like this.
Go ahead. What?
No, I just
Okay. Anyone else?
I was telling you to stop.
I'm talking about piece front. Is the front A?
Yeah.
Yeah. Okay. The front's A. Piece B we don't worry about. It's gonna blow back like this. But piece A, will it land? Will it land or closer or the same thing? It had not exploded. So we shoot one rocket. Ah, crap! It didn't explode. It lands on the ground. And we say, all right, let's fix the second one. Same angle. We shoot it. Boom! It explodes at the top. Does piece A land closer, the same, or farther than the previous rocket?
Farther, because when it's in midair, you're exerting another force on it, so it goes faster.
Very good. Well said.
That's well
okay.
said.
Do you remember and Eric was right too, remember the concept of impulse?
Yeah.
What causes a change in momentum?
Explosion.
If you remember the concept of impulse, what is it? It's F delta is delta P. Change in is caused by force exerted on an object. An object cannot change momentum unless force is exerted on it. Does this make sense? Right? And then the explosion exerts the force. So that's why it's going to land farther. Okay? And as Calvin said too, part B is going to land back closer. So that's good too. Okay? So go farther. So we can't just use our straight calculation, but what we can do is break this into two parts. And this is why this is difficult. What we have to do is find this distance, x1, and then find this distance, y. Because then if we know y and x1, then we can take the initial velocity of this projectile motion problem off the top. So now, what we have actually done is taken this problem and we've broken it down to see that it is a two-dimensional motion problem. Then it's a momentum problem. Then it's another two-dimensional motion problem, different parameters. So this is actually 3 problems in one. Okay? So, unlike, where is it? Where was that other problem? No, I guess I didn't do it. I guess I did it yesterday. Unlike the one yesterday with not the hockey pucks, the easy one. The boxes, the ballistic pendulum. The ballistic pendulum was 2 different kinds of problems in one, but that was pretty strict, worked out as just one problem. This would be pucks where it would take up like the whole test. Okay, because there's a lot of stuff going on here. All right, so how do I get this height? How do I get this distance? There's like a million ways to do this, right? What I could do is I could say, oh, I could do this. I could say it had this initial velocity here, right? The vertical velocity up here is 0, so that I can use energy. Because this loss of kinetic energy is going to become what? Up here. Yeah, potential to gravity. So I'm going to say that KE is going to become this PEG. So then that's 1/2 mv squared equals mgh. Cancel that out. H is equal to v squared over 2g. So v squared over 2g, 36 times 36, divided by 19.6. Oh, crud nuggets. Did you get 66 meters, basically? Double check.
MG.
Where? MGH.
Oh,
Remember PEG is MGH? Double check. Did you get 66 meters?
Yeah.
Whatever, 66 something. Okay, so if I know that that's 66 meters, right? We find this distance x. Well, I'm going to need to know the time that it took to get here. So I'm just going to say v is equal to v0 plus at. Because what was it that slows this down and makes it stop at the top? Gravity, right? So what I'm saying, t is equal to v minus v0 over a. v0, because that's final velocity. v0 we know to be 36, so we say negative 36 meters per second divided by negative meters per second squared. And that's going to give you, what, 3 something, right? 3.6. So that gives us 3.6 seconds. Now I can say x equals vxt, or x is 48 times 3.6. And what do you get? 48 times 3.6 is around 160 maybe? 176? Okay, so this becomes 176 meters. So the key points here, this, and we needed that. Because now we have a new problem. And this new problem looks like this. Pretend this is the new problem. You are on a 66 meter high cliff. You have an initial velocity of 48 meters. Then you explode. Your mass is 1. And this mass is 0.5 kilograms. And then this one moves backwards at negative 20 meters per second. You see, that's the new problem. Right? So first was this two-dimensional, and I had to find out and how far it went. To look at an exploding thing up there, so I have to look at this exploding part. So let's take a look at that momentum problem. Say Pi equals Pf. So what is the momentum for the explosion? Is it 0, just like last time? Good. No, right? It's the total mass. It's ma plus mb times v. Does that make sense to you? Yes? Sorry? Sure. This has this velocity at the top of the projectile flight. It's not going up and down anymore. It's just going like this horizontally. That means this whole rocket has 48 meters per second velocity. So what is its momentum? There you go. Mass, right? Okay.
Wait, you need the mass of both those?
What?
You need the mass
Of course, because it's still one piece.
Oh.
It hasn't blown up yet. Right? Remember the equal sign. The equal sign is the interesting collision problem. It's the collision, it's the explosion, it's the whatever. So now we say MA VA final plus MB VB final. Okay? We know this, we know this, we know this, we know this, we know that. Right? Check marks. We say B, VB final. Wait, no, not B. We want A, don't we? Yeah, so MA VA final equals total mass times velocity minus MB VB final, and then of course I can divide both sides by MA and get VA final. Okay, and that's going to give me, this is 2 times 48, which is 96, minus MB was 0.5 times negative 20, it's going to give me negative 10, all over the mass of A, which I believe is 1.5. So then we have 106 divided by 1.5, which should be, this is 3 halves, 106, that's 2 12s, 2 12 divided by 3.
Is it
See something? What?
MT?
Yeah, so I get 70 points meters per second. Yeah,
What happened to VMB?
what happened to what?
VMB?
V and V and,
V times M base B.
oh, this right here? Oh, this right here? Here? Here?
There.
Oh, yeah, that's mass total. Total.
You just drift velocity to the MD, and then I don't know where it went. Where'd it go?
Oh, so, okay, so this isn't, careful, this looks like distribution, but it's not. Right? This is the momentum beforehand. This is the momentum after. Do you see what I'm saying? This isn't distribution. Distribution.
Alright, got that.
Okay.
On the left.
So then what I did, yeah, and so I just took this and I turned this into mass total.
Okay.
Because I know this is 0.5 and that's 1.5, so I just made it 2. That's where I got the 96 from, 2 times 48. So now, what I know is this. I have a projectile moving 70.6 meters on a 66 meter high cliff. Question, what is x2? What is x2? So what kind of problem? Celeste, what kind of problem is this? What type of problem? So, is it specifically about energy? Is it forces? Is it collision? Is it linear motion? Is it 2D? What's that? Okay, so in a way, it's linear, but do you see that it moves in how many dimensions?
Finished.
2. It moves horizontally and vertically. Therefore, it's, whoops, I just broke it. I don't know what happened. Wait. Oh, what is this?
You want me to put in the extra credit?
I don't know what's going on.
Mr. McClure,
What?
you want me to put in the extra credit for the presentations?
This is weird. Sure.
How many points extra credit is it?
How do I get my thing back? There we go. Okay, cool. Yeah, so it's a 2D motion problem. 2D motion problem. When we talked about 2D motion, there were different types. And this is the tabletop type. Okay, so if I'm looking for x, what dimension do I start out with? Y. So then, when I remember, whenever you have a 2D motion problem, the first thing you should do is this. The two-dimensional equations, right?
How much extra credit is it?
If they get the highest, I'd give them like, was it out of, how many points out of?
The lab?
Yeah, I mean that part of it, the presentation.
Oh. Presentation is...
Okay, at this point, we now know a couple things. We know the initial vertical velocity is 0, so we can solve this for t. So we get t is the square root of 2y over g, right? And when you get that gives me the time, which I can then multiply by this velocity, right? Because that's right there, and that'll give me the distance. So this time, 132 divided by 9.8, 140 square root of that is like 11.8 or something. What time do we get? I'm guessing. Anyone? Time? Times by 9.8, square root that, what's the time?
3.6.
Good. Great. Oh, I didn't square root it, duh. Yeah, 3.6. Okay, so 3.6 seconds. Once again, yeah, that's annoying. Did I need to do this?
What?
Why did you say, who said, why'd you say that? Why'd you say that? Yeah, and we already did it. And what goes up must come down. It has to come down at the same time it went up. Oh my gosh, what a doofus. Anyways, we did it.
Actually, only 2.
We didn't really have to do it because we already knew the time. So we should have just said x is equal to 70.6 times 3.6, which will give you 230.
Is it?
To what?
258.
Oh man, I'm off today. 58 meters. Now, that's just for x2. So x total is 1 plus x2. x1 was 176 plus 258. Ding, ding, ding. And we're done. 434 meters. And that, ladies and gentlemen, is how you do that problem.
Wait.
Yeah.
Isn't 3.6 the total time spent?
No, it was just the time to get to the top.
Oh, okay.